So let's sum up what we have found. We have found an expression for t depending, we have an arbitrary constant a, expression of x with arbitrary constants b and c, but you know that these constants are going to be determined by the initial conditions and so initial condition, that's the one. So probably the thing depending on well, we're going to see that, and that's the boundary conditions. Okay. All right, so let's use those. Let's use maybe first the boundary conditions. So from the boundary conditions, we get that u of 0 t is equal to u of 1 t is equal to 0. So what does that mean? It means that for all t, the value in 0 is equal to 0. So that means that x of 0, t of t is equal to 0. So that means that x of 0 must be equal to 0. What is capital X of 0 in what we have found? It's b. Okay, b times cosine square root of lambda times 0, okay, so that's 1, and c sinus of 0, which is 0. So that implies that b is equal to 0. Okay, good, we've already gotten rid of one of my constants I have to find. Then I also have that x of 1 t of t should be equal to 0. So what does that give us? So that second part of the boundary condition, that gives us that for all t, x of 1, t of t is equal to 0. So that means that, well, x of 1 should be equal to 0. So what is x of 1? X of 1 is equal to c times sinus square root of lambda times 1. Okay, so square root of lambda, maybe I don't have to write this one. Okay, thing is that if I put c is equal to 0, I will just have x of x is equal completely to 0. So I can't I don't want the 0 solution because it might not coincide with the initial condition. So what else can I do? I can work on the lambda, because if you remember, the lambda was completely arbitrary. I said, well, those two things, as a function of t and a function of x being equal, they must be equal to some constant. And we said, well, let's put this constant, let's say that it's going to be called negative lambda, right, with lambda positive. So I can choose my lambda. So what sinus gives me 0? Well, I can choose square root of lambda to be equal to anything times pi. Okay, well, that's good. That means that so n being an integer, I can just write that x of x will be some c constant times the sinus of n times pi times x. Okay, I just substituted b by 0, which we have found, and n pi, lambda by n pi. Okay, maybe let's say that I said it could be any value of n times pi. Let's say that this is called Cn, the corresponding constant. Okay, but now that I'm here, what do we have? Okay, let's just make a small, overview. We have that u of xt should be equal to t of t, and the t of t we said was a exponential, what did we get? Minus, so lambda, I know now it's minus n square pi square k times t times cn sinus of n pi x. Okay, so let's also say that I corresponds to the n that I have, and even that the u corresponds to some specific n. Thing is that if you remember, one very important thing about linearity is that I can add any solution and it's still going to be a solution because my equation is linear. Okay, so that means that if I've got a solution that corresponds for some n, I can also have a solution for that corresponds for another n, and I can still sum them. And why stop there when I can do an infinite sum? Okay, so I'm going to write that if un of xt is a solution, then if I write the sum from all the n, so n is equal to 0 to plus infinity of those solutions, it's still going to be a solution by linearity of the equation. Okay, so maybe you're seeing where we're going. So, well, what do we have? Well, I've got an and cn. Well, let's say that as these are constants that I must find, and let's just multiply each other. Let's call that dn, right? And so that means that I'm going to have that the sum from one, well, I could start at 0, but then I would get the sinus of 0. So from 1 to infinity of e minus n square pi square kt times the sinus of n pi x is going to solve my equation. Okay, so that's good, because now I'm going to be able to fit my initial condition. Okay, so that's the next very important step. Initial condition, what am I doing with this one? It's so initial condition tells me that u of x and t is equal to 0 should be equal to phi of x. What does it imply if I have written my solution u as the previous formula? It means that I should have the sum from 1 to infinity of dn e minus n to p to kt times my sinus n pi x should be equal to phi of x. Does it ring a bell? Okay, so I've got my function phi is going to be equal to, well, something that it does not, well, sorry. If t is equal to 0, that just disappears. Well, that's just equal to 1. So my function 1 is equal to an infinite series of some coefficients times the sinus of n by x. What do we have here? That's exactly the Fourier series, the sinus Fourier series of phi. Okay, so that's how do we find the coefficients? Well, you know that the coefficients of the sinus Fourier series of phi, they will be given by 1 over 2. Okay, we say we are doing so sinus, we're doing an odd extension. Okay, so I've got my phi function, which does something on 0, 1. And I said that phi of 0 was 0. Okay, that's, sorry, u of 0 for x is equal to 0 was equal to 0. So my odd extension is going to look like this. And so when I'm doing my integral, I'm going to have this on half a period. So let's see. Okay, so the bn coefficients for phi, they are going to be, so my period is 2, so half a period is just going to be 1, okay, 1 over 1. The integral from, on my whole period, so from -1 to 1, of my phi of x times the sinus of n by x, okay, dx. And, well, these are being two odd functions, the phi and the sinus, that makes it an even function. And the usual simplification that we do is just going to be to say, well, it's just going to be 2 times the integral from 0 to 1 of phi of x sinus of n pi x. Justification of that is that this function, as the product of two odd functions, that makes it an even function, and so the integral on the interval -1, 1 is just going to be 2 times the integral between 0 and 1. Okay, and so this is it. The Bn coefficients for my function phi, my initial condition, well, it's just going to correspond exactly. That's what we were looking for. That's the Dn coefficient, right? And that's what we just want. The last thing we needed to find, and so I've got my u of xt is going to be given by the sum from 1 to plus infinity, and here you have that Fourier series of so my coefficients 2 times integral between 0 and 1 of phi of, maybe let's not take x as a variable of integration, let's take not t, let's take y, phi of y sinus n pi y dy times, so that's my coefficient, times my exponential minus minus n square pi square kt times my sinus n pi x. Okay, so this is it. I hope I haven't, yes, this is exactly what we wanted. So that's my this is my solution. All right, so don't learn that. Of course, don't learn this by heart, but you have to know exactly how to find this. Let's just take a very simple example of initial condition. Okay. Sorry about this. Example, if we have phi of x, let's take a simple one. Phi of x being already a trigonometric function. Let's take sine of pi x. Okay, so it's also equal to 0 in 0 and 1. All right, so you know that the trigonometric series of phi, well, as it is already a trigonometric function, it's just going to be itself, right? So and it just has one coefficient. A1 is equal, so it's not A1 according to my notations, just the B1, which was what we call the D also above. It's just going to be 1, and all the others 0. So that finally your solution would be u of xt sum of well, 1 times, I don't have any sum by the way, so that's the point of this example, exponential minus n square pi square k times t sinus of pi x. I still have something even. And it's only valid for n is equal to 1, so this is the one we have. N is 1, so pi square kt times sinus of pi x. Okay, and we see that if this is the kind of profile we started with, so between 0 and 1. Your profile was the sinus of pi x, so that's your initial condition, phi of x. Well, it's just going to decrease over time and just stabilize to so as the t increases, that exponential is going to get smaller and smaller times well, the same profile, so it's just going to go to a flat profile equals to 0 everywhere.